Differently abled people have always faced a constrained independence. Though society has always had concerns for them, it is only recently that there have been vast improvements in their lifestyle. However, such benefits have been restricted to the affluent. Participating in TI India Analog Design Contest 2012-13, we wish to develop a feasible solution to help the differently abled. Our idea is a solar-based, hybrid electric-powered wheelchair. Solar panel. With around 300 clear, sunny days in a year, India has vast resources of solar energy to be utilized. The solar panel used is BP580, manufactured by BP Solar. Solar charging module. This module proved to be the most challenging in our design, with majority of our innovations and analog sub-modules involved with it. We decided upon a single-ended primary inductor converter, SEPIC, to charge the battery. Despite literature citing disadvantages of complicated design and pulsating current, we went ahead with SEPIC for these strong reasons. First, it has buck and boost operation. Second, SEPIC provides non-inverted output. Third, SEPIC has minimal active components. The design was first verified with a MATLAB simulation. Inductor current does not fall to zero. The power from the solar panel mounted on the wheelchair is the input to SEPIC. The panel current is seen on the ammeter. The SEPIC is interfaced with current and voltage sensors. The panel input is fed to SEPIC. The MOSFET is driven by the PWM pulse from the MSP430G2452 via the gate driver circuit. We have used multimeters and ammeters to verify the circuit's operation. The output from SEPIC is connected to the battery. EPP algorithm. The battery voltage is continuously monitored, and as long as it is below 80% of its full charge, the battery is charged at maximum power point. Maximum power point tracking is an implementation of the maximum power transfer theorem. Charging the battery at maximum power improves the system's performance. The simple perturb and observe algorithm fails to track the maximum power point for rapidly changing irradiation levels, as in the case of a moving vehicle. Our project required an MPPT algorithm with fast convergence, and our research led us to the estimate perturb and perturb algorithm. The estimate perturb and perturb algorithm operates in three modes, with one estimate cycle for every two perturb cycles. Hence, the accuracy of maximum power point tracking is enhanced without compromising the speed of tracking. The EPP algorithm is implemented in the MSP430G2452 with inputs from the sensors. With an op-amp subtractor circuit, the potential difference across a resistor is measured, with V by R giving the current flowing through it. LM358, a single supply op-amp from Texas Instruments, is used for this purpose. The panel current and the panel and battery voltage are measured in our project. The analog output from these circuits is digitized by the MSP430G2452. The voltage sensor is a simple resistive potential divider circuit. The voltage output from MSP430G2452 is not sufficient to drive the gate of the MOSFET IRF540. Thus, we use a gate driver IC IRS2110. However, its output waveform got distorted on loading because of insufficient current from the microcontroller. So, we integrated a Darlington amplifier to boost the current and ultimately obtained successful continuous operation of SEPIC. To control the surges in drain to source voltage waveform, we resorted to a resistor capacitor diode snubber. After overcoming the stiff challenges posed in circuit design and hardware realization, we got the battery charger module up and working. Around 35 watts is extracted from the panels. The panel current and voltage were measured and boosted by the converter. The battery is being charged through SEPIC at maximum power point. To increase the battery life, when the charge exceeds 80% of full charge, the battery is no longer charged at the maximum power point. Instead, it is charged at around 1 ampere. AC charging. To provide a hybrid feature to the system, facility to charge from AC supply has been integrated into the system. A ready-made SMPS module was hacked and interfaced with the battery via an overvoltage protection circuit. The overvoltage protection circuit uses a resistor to prevent the SMPS voltage from imposing itself on the battery and a diode to prevent reverse current. The circuit has LM358 acting as the comparator. The reference voltage generated from a Zener diode is compared with the scaled-down battery voltage. If this exceeds the reference voltage, the relay is triggered, which disconnects the battery from the SMPS. Here, the protection circuit is tested using the RPS. The LED glows when the voltage exceeds 12.8 volts. Navigation and voltage indicator. This module includes LM317, a variable linear voltage regulator from Texas Instruments to provide power supply for the microcontrollers. The joystick is used to control the wheelchair. The control signals from the joystick are processed by the MSP430G2452. LM3914 dot bar LED display driver from Texas Instruments is used to indicate the battery voltage level to the user. The circuit is calibrated to show full indication at 13.2 volts. The motor control signals are given to the DRV8432 motor drive evaluation module from Texas Instruments. This evaluation module, which supports a 7 ampere continuous output current, easily handles the 5.1 ampere full load current demand of the motors. An emergency brake has been provided to stop the vehicle if the need arises. The vehicle uses a differential drive for steering, which permits 0 radius turns. Mechanical design. Our prototype is built on a plywood base. It is rear wheel driven and has 2 free wheels in front to support it. Geared heavy-duty permanent magnet DC motors were used. The solar panel is supported by an aluminum frame. The joystick and charge indicators are placed on the armrest. The dead weight of the wheelchair is about 20 kilograms. The height of the wheelchair is comparable to that of a small car. The chassis was completely designed and constructed by us. Testing and results. The onboard SEPIC was successfully tested and it charged the battery on the run. The panel current extracted during the operation of SEPIC is observed. The performance of the wheelchair operating with solar charging for 20% battery drain is compared with that without solar charging. The rate at which the battery is discharged is less when the panels are connected, thus prolonging the battery's life. A filled water can weighing 15 kilos was used as payload to conduct the load test on the wheelchair. It moved the load comfortably. We have successfully completed the intended prototype of a solar-based hybrid electric powered wheelchair and have found improvement in performance due to solar power. In the future, we wish to include state-of-charge based battery management system and industrial grade motors.